Anybody have any questions you'd like me to go over on the vector review? Okay. So yeah, that's due on Friday, at midnight, basically Friday night. And you have an extra day if you don't get it done by then. But feel free to bring questions on Friday if you have them. But otherwise, I'm just going to start going through the mathematical preliminaries. Yes?
For the vector review, should I turn it into both classes?
Oh, no, you can just do one or the other.
Okay.
Yeah.
Should I just leave like a comment?
No, I know who's in what classes yet. Okay, so in this class, the key mathematical preliminaries are matrix-related things. So okay, so when I write a matrix, like when I write a vector, I put the over arrow on it to indicate it's a vector. When I write a matrix, I'm going to give it the under squiggle like this. And so as an example, let's say you have the matrix 2, 1. Oh, and when I read it out loud, I'm always going to go across a row and then down to the next row down. So when you hear me reading off numbers, that's always the way I'm going to read them off. So 2, 1, negative 2, 4, 0, negative 6. And the first thing that you have to know in talking about matrices is how to describe the size of this matrix. You always give the number of rows first. So the size of the matrix is the number of rows by the number of columns. So this one is a 3 by 2 matrix. And if I want to describe specific elements in a matrix, I'm always going to, so the subscripts that I use are always going to be the row followed by the column. Okay, so in this example above, and I'm always going to use a lowercase, like I'll always use a capital letter to represent a matrix, and then the elements are going to be that same letter but lowercase. Okay, so A11 is 2. A12, because it's on the same row, different column, is 1. The negative 2 there in that matrix, what would be the subscripts for that?
2, 1.
Yeah. 2, 1 is negative 2. 2, 2 is 4. What would be the subscripts for the negative 6 there?
3, 2.
Yeah. And 3, 1 would be 0. All of these matrix calculations, I'm going to tell you how to do these calculations, but and it's important to understand how these happen, but really you just want to do them in your calculators. So to enter a matrix into a TI calculator, If you have an 83, a TI-83 or a TI-84, you can go into the matrix environment and then go to edit. Okay. If you have an 84 or an 89, you can enter it as, so an outer square bracket for the whole matrix, and then square brackets marking the beginning and end of every row with a comma separating the things inside the row. So this would be, I'm going to use this matrix I did above. So 2, 1 is the first row. Then the second row is -2, 4. Then the third row is 0, -6. Square bracket to end the third row, and then another square bracket to end the matrix. If you have an 89, you can use a little bit faster one where you do a square bracket for the matrix. And then to separate the rows, use a semicolon. So 2, 1, semicolon, -2, 4, semicolon, 0, -6, and then ends matrix. So on an 84, you have 2 options. On an 89, you have 2 options. I think this is also, this first one is how you have to do it if you have an 86. I don't know if any of you guys have 86s. They don't seem to sell those anymore. And then the other one people would have is the Inspire, the very poorly spelled Inspire. And to do that, you go to, there's a little button on the right side that looks like, I think these are supposed to denote like matrix elements. And then you have to tell it what size you want. And then you just enter it in the keypad. It's sort of clicky, but it is pretty quick and efficient. Give me that. So there are 4 important matrix sizes for this class. The first one is a 3x1 matrix, and that's going to represent vectors. In 3D. In this class, just about everything is going to be 3D rather than 2D. So, yeah, I don't probably have to give you an example of this, but I will. So the force vector could be like 10,000, -15,000, +5,000 in newtons. The second type is a 6x1 matrix. And we'll use this as the Voigt form of stress and strain. So we'll represent stress a couple different ways. Strain will always represent using this Voigt form. And so the Voigt stress, and I'll represent it with an under squiggle like that, could be 1.5 times 10 to the minus 5, 0, 0, negative 6 times 10 to the minus 6, 0, 0. And while this is up here, might as well start getting used to like what kind of values we're going to see on stuff. Strain values are always going to be really small like this. If you ever get a strain value bigger than 1 times 10 to the minus 4, then it's mathematically, it could be right, but it's not physically realistic. And also, notice that there's no units on strain. Strain is going to be a unitless measure of deformation. Okay. Third is a 3x3 matrix. And we'll use this for stress tensors. That's the second way we'll represent stresses. And this will also be the size of our rotation matrices. And so for a stress tensor, we'll usually denote it with the Greek letter sigma. This is epsilon, by the way. So the stress tensor is a sigma with an undersquiggle, and a possible stress tensor would be like 6 times 10 to the 6, 0, negative 8 times 10 to the 7, 0, 5 times 10 to the 7, negative 2 times 10 to the 6, negative 8 times 10 to the 7, negative 2 times 10 to the 6, negative 5 times 10 to the 7. And the SI units for stress are pascals, like units of pressure. We'll also a lot of times report stresses in megapascals or even gigapascals. So be sure that you're clear on what unit you're using and make sure that you don't have a unit mismatch in your calculations. One thing to notice about this, okay, I haven't defined this yet, I will, but this is called a symmetric matrix. And what that means is think of everything across the diagonal from, like, if you think of this as like a reflection across the diagonal, all of these reflected elements match each other. Okay, the 0 and 0 match, negative 8 times 10 to the 7th match, negative 2 times 10 to the 6th match. Okay, and that's always the case with stress tensors. This is always true for stress tensors. We'll see why physically in the next day or two. And then the last one, unfortunately, that we're going to see a lot is a 6x6 matrix. And this is the reason why you're going to want to do these calculations on a calculator instead of by hand. I mean, this would just be brutal to do these by hand over and over again. And this will be for the compliance matrix. I'll call that C undersquiggle. And for the stiffness matrix, and I'll call that E under squiggle. And one thing about these is they have the same information. It's just two different ways of using it, and they're the inverse of each other. So C is the inverse of E and vice versa. And it might seem pointless to write out 36 values in this matrix, but I want to give you a first glimpse at one that we're going to see over and over again. So the compliance matrix has the elements 1 over the scalar E, negative Greek letter nu over the scalar E, negative Greek letter nu over the scalar E, 0, 0, 0, and then negative nu over E, 1 over E, negative nu over E, 0, 0, 0, and then negative nu over E, negative nu over E, 1 over E, 0, 0, 0. So that's the first 3 rows. And notice the pattern there. In every one of these rows, you have a 1 over E and 2 nu over E, take 2 negative nu over E, and the 1 over E just keeps bopping along to the right each row. Okay? And then we have a new pattern for the last 3. So we have 0, 0, 0, and then 2 times the quantity 1 plus nu over E, 0, 0. And then that one just keeps bopping along to the right. So the next one is 0, 0, 0, 0, 2 times 1 plus nu over E, 0. And then finally 0, 0, 0, 0, 0, 2 times the quantity 1 plus nu over E. And the usefulness, the way we use this compliance matrix and the stiffness matrix is that the Voigt form of the strain is equal to the compliance matrix times the Voigt form of the stress. And because of their inverse relationships, the Voigt form of the stress is equal to the stiffness matrix times the Voigt form of the strain. So in this class, always, if you know the strain or you know the stress, you can calculate the other one. If you know, basically, these are material properties that represent a certain material. Okay. So like steel, for example, in the range of deformations that we're working with in this class, you could fill out this compliance matrix for steel. And then if you know what the stress is you're applying to the steel at a point, you can use this matrix to calculate what the deformation would be. Stress is like a set of loads on a point. Strain is a set of deformations on a point. Okay, here are some important matrix definitions. The first one is the transpose. And so if you have a matrix B that's the transpose of a matrix A, what that means is the element ij of A is equal to the element ji of B. This should be lowercase b. Okay, so you can imagine it's pretty easy to write a little computer program that'll take the transpose of a matrix. As an example of what this looks like, so if you have a matrix A that's equal to 1, 2 in the first row, 3, 4 in the second row, 5, 6 in the third row, then the transpose of A is everything that was a row is now a column. So the first column of this transpose matrix is 1, 2. I'm sort of breaking my rule for how I read these off, but I'm just trying to make it clear what a transpose is. The second column of the transpose matrix is 3, 4. And the third column of the transpose matrix is 5, 6. And you can see that the index by index thing works too. This 4, for example, in A, that's a terrible example. Let's do the 3. Okay, the 3 is element 2, 1 for A. Okay, and it's element 1, 2 for A transpose. You can see that what we've done is just switch the order of the subscripts. Okay. So one thing to notice is that the transpose of an M by N matrix is an N by M matrix. Okay. Any questions about that? Oh, one thing I want to say about that for putting it into your calculators is TI calculators have that as a built-in function. All of them do. And it's like a exponent capital T. And one thing, I'll say this now, I'll say it again later, but the inverse of a matrix is not the same as the transpose. Has everyone heard of an inverse matrix before? Anyone not heard of an inverse matrix before? Okay, so, well, let me just put that in as a second one here. So this is transpose. Second, the inverse of a matrix, the definition of it is if you take a matrix and multiply it by its inverse, and the inverse is looks like to the exponent of -1, you get the identity matrix. which is ones down the main diagonal depending on how many elements you have. And it's called the identity matrix because if you multiply it to a vector of that size, you get the vector back. And also, you can go in the other order. A inverse times A is equal to the identity matrix also. Okay, and the reason I brought this up is that the inverse and the transpose are different. But they equal each other for rotation matrices. Okay, so, we're going to use transpose all the time with rotation matrices, and what we're really doing is taking an inverse of it. It's really true for all matrices of the type orthogonal. All orthogonal matrices, the transpose is equal to the inverse. Okay, what number are we on now? Okay, the third one now is, and what about doing inverses in a TI calculator? You can just raise a matrix to the power of -1 and it'll compute that matrix for you. That's cool. Okay, the third one is a square matrix. I think if you had to guess what a square matrix is, every one of you would guess right. It has the same number of rows as columns. So it has the same number of rows and columns. For square matrices, the diagonal elements have indices where I is equal to j, and the off-diagonal elements are the ones where I is not equal to j. Okay, so for example, if we have a matrix 2, 6, -1, 0, These are the diagonal elements. And these are the off diagonal. And then for a symmetric matrix, it has to be a square matrix. There's no such thing as a symmetric matrix that's not square. So this is a square matrix. Where every Aij is equal to Aji. Another way of saying that, so in other words, i.e., the matrix A is equal to its transpose. One really useful thing about symmetric matrices notice symmetric matrices always have all real eigenvalues. Okay, so we're going to do a lot of eigenvalues and eigenvectors, and we won't get into that for a couple weeks, what that means, but the main, in this class, I think the only eigenvalues that we're going to use are eigenvalues of the stress tensor. Well, the stress tensor always has to be symmetric, I said up above. So the eigenvalues that we're going to get out of the stress tensors are always going to be real. And that's going to have, that it's going to have to be the case because when we talk about what those eigenvalues represent, it's like imaginary ones wouldn't make any sense. Okay. All right, so anybody have any questions about this run through matrix definitions? So now we have to talk about what matrix multiplication is, how to do matrix multiplication. So you can always think of matrix multiplication so matrix multiplication is a series of dot products between rows of the left matrix and columns of the right matrix. And in fact, we're used to dot product notation like this. So let's say we have a vector 2, 1, -2, dotted with a vector -5, 0, 6. But we can also always write a dot product as a matrix multiplication. if we take the transpose of the left matrix. Okay, so we'll take the transpose of this, and now we can write this as the matrix multiplication 2, 1, negative 2 times negative 5, 0, 6. Okay, and so to calculate that, then it's 2 times negative 5 plus 1 times 0 plus negative 2 times 6, and I think you get negative 22. So let's do a 2 by 2 example. Let's do 1, 2, 3, 4 times 5, 6, 7, 8. Okay, and so these dot products are going to give us, so we're going to take the ith row of the left matrix and multiply it, dot product it with the jth column of the right matrix, and that's going to give us the ij element of the product. Okay, so first I'll take the first row of the left matrix and the first column of the right matrix. So that's going to give us the element 1, 1 in our product. Okay. I'm about to erase these circles, but see what I'm multiplying there. So this 1, 1 element is going to be 1 times 5 plus 2 times 7. And now I'm going to multiply dot product the first row with the second column to give us the 1, 2 element of the output matrix. So that is 1 times 6 plus 2 times 8. And now I'm going to do the second row of the left with the first column of the right. And that's going to give us our 2, 1 element. And so this is 3 times 5 plus 4 times 7. And then last, I'm going to do the second row with the second column. Hold on a sec. Yeah. I'm going to miss that, though, when I get a new computer. It gives us just time to take a little stock inventory on our lives. Yeah. Yeah. Okay, so now this is 3 times 6 plus 4 times 8. And so what's that? 19, 22, Seems right.
$53.
25,
32 plus 18.
28.
32 plus 18.
Oh, no, I did my numbers wrong.
Okay. Okay, well, I mean, you should understand how this works, but I'm not going to ever make you do it by hand in this class. You're just going to, I mean, it's so much easier to just punch these into a calculator. And you can imagine, I mean, it's hard enough doing doing 2x2 matrices. Imagine 6x6 or whatever, you know, it'd be horrible. But remember that the ij element of the product matrix is the dot product of the ith row of the left matrix with the jth column of the right matrix. And in a TI calculator, so in TI calculators, once you have those matrices entered, you just use the regular multiplication symbol. And it'll do it for you. Okay, there are a few things I want you to notice about this. So matrix multiplication between two matrices doesn't always exist, okay? There are conditions that need to be met. Because you can't take a dot product between two vectors that have different dimensions, right? So for a matrix product to exist, the number of columns of the left matrix has to equal the number of rows of the right matrix. Okay, this is the first one. First thing to notice. The second thing to notice is if the left matrix is the size m by I, and the right matrix is the size, well, in order for these to have a product at all, we have to know one of the parameters of the size. Which one would that be? I didn't hear that, but I'm going to assume, yeah, I, that's right. So the right matrix then would have to be I by something. Let's say that it's I by n. Then the product matrix is m by n. Okay? It's easy if these are square matrices, then everything, if they're square and they're the same size, you can multiply them, and the output is going to be a square of the same size. The third thing to remember is that order matters. A times B is not equal to B times A in general. And A times B can exist, and that doesn't even guarantee that B times A exists. And then the last thing to keep in mind is that grouping doesn't matter in multiplying these. So if you're multiplying the matrices A times B times C, you can do that as first doing A times B and then multiplying it by C. Or you can do it as first multiply B times C and then multiply what you get times A. You just have to keep their positions the same. Okay, you couldn't do it B times C and then have A over here on the right. That would give you a different answer. Okay, any questions about that? All right, that's it for today. You have the vector problems to work on, and I'll think about whether to give you something like this to work on too. But